Okay, we are we are live. How is everybody doing today? First of all, you can either use. By the way, you can use the live tutorial chat in the live tutorial chat or the streams embedded chat. Doing good. That's good to see. So, damn, we got actually a reasonable amount of people. So, I am, by the way, I am perfectly fine with you guys miking questions in if you want. That's part of the reason why I have this in a VC and not a stage channel. But do keep it like relatively, like be respectful with it. Don't constantly like do audio spam. Anyways, that's enough of intro. I say we get started, eh? So, first of all, can everybody can see my screen, right? I think I'm sharing everything. Well, all right, cool. So, basically, we are going to be talking about Raymarching today. So, basically, well, what is Raymarching? So, there's a couple different ways to render a 3D scene. One of those ways is called ray tracing, which you're probably most familiar with. That's what Blender uses. There's also rasterization, which is like a real-time one that a lot of games use. But then there's this odd middle child called Raymarching, which is not used like basically at all, but it's by far the most elegant of them, I'd say. But also it's the most difficult to work into a regular pipeline, and you'll see why in a second. So, with ray tracing works based on you're calculating precise intersection points between a ray and a plane, right, or a sphere, or any mathematically defined solid, right? So, for instance, I know this isn't like real like ray tracing preview, but if we're doing ray tracing, we'd shoot out a ray and we calculate the point at which it hits the surface, and then we compute the interaction with the surface, and we'd update the ray based on that. So, for instance, we'd update the direction and a couple other things that go with it. In fact, you can implement ray tracing in Blender. Let me open a file I have. You can do ray tracing inside the world shader. And basically, this is fun because it's very modular. So you can literally just iterate these light samples, which is essentially just light bounces, and you can get something neat. But this is very good for just a general approach to rendering a scene, right? Because you can find intersection functions really easily, and you can combine them into a scene intersection function, this is a lot of math for a relatively simple thing. But you can use these to combine like a plane intersection function with a sphere intersection function and all that jazz. And by the way, I will expand on all of this later. This is going to be its own separate video because I think it's a cool concept. But Raymarching is a little bit different. So, Raymarching is a far more iterative process. So, instead of directly calculating the intersection point between a ray and an object, or a ray and the scene, you find a distance function and you march a ray based on that distance function. So let's do a simple example. So if we get our ray's direction, So you can find that in the geometry. The incoming tab will give you a ray direction. So basically all that means is that this output of this geometry node, it's going to be colored according to which direction we're looking at, because the camera shoots out like millions of rays, one for each pixel. So for instance, if we're looking down, we actually technically have to invert this because it's showing the direction from the point to the camera. Let me grab a vector math. So actually it's easy, it's going to be easiest to see if I do this in the world nodes. Sorry, I should have gotten this set up beforehand. Alright, anyways. Alright, so you can see when we're looking up, it's very blue because the Z direction is blue. When we're looking down, it's not blue at all. Same with red and yellow for X and Y. Or sorry, red and green. So basically, the principle for Raymarching is that we are going to find a distance function between our camera and the scene, which means just the objects in the scene. So that means we're going to find the closest point, which is actually technically this is called the distance estimator. So we're going to find the closest point, we're going to find the distance to the closest point away from the camera or the ray's origin, and then we're going to march the ray by that distance. And because the distance estimator is going to return the closest distance, it will not go through the object, and we can keep iterating that. And I'll show you a graphic on how that is. So let's do this Raymarching. I'm sorry, I should have gotten all this set up beforehand. This is very complex. Alright, here's the one that I usually use. So you can see, let me open this in the tab. So we can see if we start our ray here, we find the closest point, the distance to the closest point, then we march the ray in a certain direction, and then we reevaluate the distance, and then we march the ray by that amount, and we keep doing that until we get within a certain tolerance of the scene. So this one graphic did a lot better than me trying to explain it. But anyways, so for this to work, we need to find two things. We need the ray direction, which is going to be the direction we march, and we need the distance estimator. So we have one thing here, is the ray direction. Now we need to find the distance estimator, which is this, going to return this function for the radius of this circle, which is the largest circle that doesn't intersect anything, as you can see. So I'm going to pause here for questions, because I know I didn't explain that very well. Let me see if there's anything in the chat. Yes. Our first, yes. So obviously, well, not obviously necessarily, but the first thing that you want to find in any, by the way, I don't think I have my desktop audio. No, so I'll repeat the question. So the question is are we finding the ray bounces right now? Wait, sorry. Could you repeat your question? Yeah. Okay. Okay. So yeah. So the question here, I'll just answer, and that'll hopefully um, give people watching on the YouTube end a good impression of the question. So basically, instead of trying to find the exact intersection point, we're using an iterative function to approximate that with a high degree of accuracy. So that's the main difference. So we're going to calculate light bounces later, but the first goal of any rendering engine is to find the intersection point. That's when you can find the bounces. That's how you find the bounces from that intersection point. All right. Let me go back to Blender. So let's start with a simple implementation. So we have our ray. We have our ray direction. This is the direction that we're going to be marching our ray. Next, we need to find the distance estimator. So I'm just going to do the simplest distance estimator there is, and that's going to be for a sphere. A sphere is fun because it's like pretty much like universally symmetric. So that means that the distance estimator is very simple to create. So if you start at a point, the distance estimator is just here, I'll just put it in math. I'm a bit out of practice with explaining it. So if we get vector math, we can find like the distance. So a sphere is characterized by the set of all points that are equidistant from a certain origin. So that means that all of the sphere's points, that we take a length of them, this length function, or more accurately the distance function, between a point on the sphere and a certain point, it will always return the same value. So if we take, let's say we have a sphere, we can use a combine XYZ, and this will be our sphere's origin. So if we have a point on the sphere with radius 1, this distance function, if we input that point here, will always return 1. So basically what that means we could do is we could find a very simple distance estimator by taking an input point, which is just going to be, I'm just going to use this. I'm going to say, let's say we're looking down at it. And we can take the distance here from this to the origin and then subtract the radius of the sphere. So I'm going to subtract the radius, which is going to be this value, and I'm going to make sure I label these. So this is going to be the radius. I'm going to just set that to 1. This is going to be the ray origin. This is going to be the sphere origin. So basically, if we want to have a sphere with a radius of 1 and we want to find the distance between a point and just any point in space and then the closest point on that sphere, we can find this ray origin. We take this ray origin, we take the distance between that point and the sphere origin, and then we subtract the radius. So basically we can see that if we have a point which is like 0, 0, 1, and we have a radius of 1, this distance is going to be 1 because the distance between this point, the ray origin, and the sphere origin is 1. And then we subtract the radius, so it ends up at 0. So that works. And then if we have this at 2, this distance outputs 2, and then we subtract 1, that's going to be 1. So we can find that the closest point, or that we are 1 meter away from the sphere. So let's put this into a node group. These are going to be our inputs. Although these are going to stay consistent, so these are going to remain inside the node group. And this is going to be outside because this is going to change, because we're going to be updating our array each time, right? Because array origin starts right here. Then after one step it moves here, then over here, then over there, right? That's what we're updating. So I'm going to group that. I'm going to call this our distance estimator. And I'm going to output the distance. So I'm going to call this vector. This is going to be the position in. And then this is going to be the minimum distance. That's going to be an output. So I'm going to put out. And then this is what we're going to use to, this is where we return the radius of these sort of spheres that we're going to be marching our array along. And the goal here is that we're going to start to see, after a number of iterations, we're going to see a sphere form out of these iterations. And you'll see what I'm talking about. It's going to sort of shrink wrap around it. It's really neat. So this ray origin is going to be replaced by our camera origin, which we can find by using a vector transform, setting it to point, camera, world, and set this to 0. This is just a universal way to find just the camera position. Not this camera, mind you, the camera that we're looking through in the viewport right now. And that's going to be the position in. Then we need to make a function for Raymarching steps. So we need, I'm going to name this. This is going to be the ray direction. So this ray direction is what we're going to be, the direction along which we are marching. So if we're going to implement this, we need to find the point, and then we need to add to that point a vector proportional to the direction that it has the length of the distance estimator. Basically means we need to add a certain vector to this point that is the distance estimator multiplied by the direction. And that's going to be our step. So we're going to add the vector, which is going to be the direction vector multiply, or actually in this case we're going to scale. So this is going to be our input. So this is our input position, and then we're going to add this value to the output. Or what am I saying? We're going to add this value, and then that's what we're going to get out. So let me group this. This is going to be a Raymarching step. So now we're going to iterate this. So I'm going to add like 8 iterations or something just to sort of see how it looks. Isn't that cool? We get this sort of sphere. And I want to show you what it looks like just as we preview just different ones. So it's going to start out, it's going to sort of, like, as I said before, like shrink wrap onto that. And we're going to need probably at least 16, maybe 32 before you can see it. And there's some weirdness in the background. You can cut that out by using by just sort of masking out any areas at which the length of the vector is too big. So if you use a vector math and length and just say where's the greater than? Oh, less than like 1,000 or 100, whatever. And then just scale this output by that. You'll get sphere. Yay. Actually, technically, we want it to be like, we can set it to like less than 5 or something. So we can see it's certainly less precise than a like a traditional ray sphere intersection function. Let me show you what that looks like. We're gonna append from this. Where is it? There we go. So this RSIF, this ray sphere intersection function, this is approximating the close intersection. So we need ray origin. Let's grab our ray direction. Then close intersection. So you can see this is certainly more precise. So why would we ever use Raymarching? The answer to that question is, we'll get to that. Because this, with enough steps, will mesh very nicely onto a sphere, and we can see it's already getting there. But we can also use really neat processes to deform this. So for instance, what if I do something like I want to add in a little bit of noise? So I'm going to add in a noise texture. I'm just going to change the detail down. And then I'll subtract a 0.5 so that we aren't shoving it in. Then I'll add a little bit of a multiply. It's going to take a little while to update. Ew, my bad. That wasn't that cool. Now we've got this more complex 3D shape. Maybe we can add in some detail there. And check this out. We can now map something like a noise texture onto it. Actually, I'm gonna isn't that cool? And we can mess around with this to make it more deformed, less deformed, anything. We can change the scale up, we can add more detail, roughness. It's pretty cool. So this is why this method is you could see how it would be useful in some situations, but also why it wouldn't be useful in something like a game where you need a lot of precision and you don't really need all these complex sort of things. But we can have some more fun with this. So now that we've got our ball, we can actually find the normal vector of this thing, which is super neat, which will allow us to get into shading it. So I'm going to pause here for questions, and then we can go on, and I'll show you how to sort of shade this like a sphere, and it's pretty cool. Or not like a sphere, like an actual object. Yeah, Dennis could. Yeah. Yeah, primally. So, yeah, it's actually really crazy how easy it is to integrate multiple objects into the scene. I'm not going to get into that this time, but essentially the premise of that is you can just, since you're finding the min distance, or the minimum, the closest, what am I trying to say? The minimum distance at a certain point. If you take the minimum of two distance functions, you can combine both of them into the scene. Let me check. Tutorial chat. Or the streams chat. Anyone else? How is this going for you? Is there anything you guys want me to retouch on? No? Yeah, it's a really elegant method. Unfortunately, it's not used. The main node group. I'm assuming you mean the Raymarching step, this one. So this ray direction is gotten by that. You can also find applications for this in parallax. So for instance, if I... oh, I have to do that. And you go to my channel. So, a while back, let me find the video. So back when I did this, you'll see in some areas you can see the parallax, like the mountains shooting through the atmosphere. That was done with Raymarching. It's a little bit of an augmented form of it, as you have to work on a sphere. But you have to work on a ray traced sphere more or less. But that is an application of it, which is pretty neat. Let me check the streams chat. Alright, I'm going to assume everybody's good. You want to see the distance estimator again? So that's just... So this is the sphere distance estimator. And then this is the noise on top of it. If you guys are curious about individual nodes, I'd encourage you to watch this later when it gets uploaded onto YouTube. I'm actually going to upload it onto YouTube this time, not like I think last time where I forgot. Anyways, let's get on to how to shade this thing, like how to compute the normals of it, because that's probably the most interesting thing. So this is going to involve a little bit of calculus. So some of you might not precisely understand. Well, actually, it's derived from just regular slope formulas, so you could probably understand with just algebra. All right. Anyways, though, I'm going to get started. I'll pause for questions a little bit more frequently, but yeah. Okay, so to calculate normals, we need to do a few things. We can actually use this distance estimator is going to be what we're going to be using to calculate the normals. So the premise is that we want to evaluate the direction a plane is facing at that point. Or not a plane, sorry, a surface is facing at that point, right? That's how we compute normals. But we don't have any information that will lead us to figuring out how that is. We don't have the precise intersections that we get when we have stuff like ray tracing. So it at first seems a little bit counterintuitive that we'd even be able to get normals from this, but it's actually pretty simple. And that's because this distance estimator is a continuous function, if that is presuming any augmentations you add to it are continuous. So that means that when we intersect with the surface, we can assume that if we change our distance by a little bit, we're going to get a little bit of a different value for the distance estimator, but it's not going to be wildly different. So we can use dx, dy, and dz, these sort of calculus things. We could just march the ray by an incrementally or an extremely small amount, and then reassess the distance estimator and use the derivative formula to get that nice normal. So we're going to get the distance estimator. Let's pull that up. Now I'm going to make this function. So let's say we have, I'm going to make this function separately. So let's say we have a combined xyz. This is going to be our position n. And what we want to do is we want to evaluate 4 separate distance estimators. So one is going to be directly at this position in. Another is going to be at position in plus a little bit in the x direction. So let's add that. So I'm going to add like 0.0001 in the x direction. And then another one would be the same thing, but a little bit in the y direction. And I'm going to set this back to 0. And then we're going to do the same thing in the z direction. Set this to 0. Sweet. And then we're going to subtract this distance estimator that we just got from this position in. We're going to subtract that. Alright. It actually works either way. We can just negate it afterwards. We're going to subtract each of these from this. And let me move this out. And then we can use a combine XYZ node to combine these all into one vector, which will be our normal vector. So the x1, this one that we're marching on the x, is going into the x, the y is going into the y, the z is going into the z. And then we're going to use a vector math normalize, because these are normal vectors, so they're just meant to be directions. They don't need to have magnitudes. Then we are going to group those and then set this as an output. So that's could be position in, and then normal out. I'm just going to call this normal computation. So we're going to use we want to evaluate this at the surface, so we're going to use this final Raymarching step. And then this is going to be the normal computation, and we'll see. Hopefully, it works. It's looking a little bit funky right now, and we might actually, yeah, we should invert it. I'm going to scale it by -1. So it's obviously not perfect, right? And more steps will fix that, by the way. But you see, roughly speaking, where it's pointing up is where it's blue. It's pointing, or it's green where it's pointing in the Y direction, and it's red where it's pointing in the X direction. So now if we want to say add direct lighting to this, we can do that pretty simply by just taking the dot product of this and some arbitrary light value. So we're going to use our arbitrary light direction. We'll just combine X, Y, Z, say its faces down, and then we're going to do a dot product. And then we can multiply the color of this, which is, we need to multiply. Actually, more accurately, scale. And we can see we get this nice shading that's only a little bit crazy from the edges. And I'm going to actually normalize this. That way we can mess with directions a bit easier, so we can change the right light direction, all that fun shit. So that is sort of Raymarching 101. I'm wondering if I should, yeah, fuck it. Yeah, this will be quick. But I want to show you guys another thing, but I should probably pause here for questions. Primarily, you say you can use a normal node for, yeah, you can. This is force of habit. Yeah. Alright, if you guys are good, I'm going to move on. So, the next thing I'm going to do is I'm going to add, or I'm going to show you guys how to add contact shadows. Which is really surprisingly easy in this, by the way. It's actually crazy. Because, well, it's pretty easy in anything when you have a distance function. Or, sorry, an intersection function, which this is our intersection function. So we can duplicate this, and what we basically need to do is we need to march this, instead of in the direction of the camera rays, we march it in the direction of the light rays. So actually our position N is going to be the intersection position. So now the thing that we're changing is going to be the direction. So I'm going to, instead of using this default ray direction thing, I'm going to add in a new input, which is going to be direction. And I need to, oh, I'm such an idiot. Direction in, and we call this position out. And I also need to add a direction out. You don't technically need to do, but it's neater that way. And unfortunately, that means we also have to connect all these up, which won't be too bad. I accidentally Control-Shift-D there. There we go. There we go. Alright, now for this we can just simply reuse this redirection thing that we got because we want this to remain the same. But for this next one, what we're going to need to do is use the position in, but we also want to march it in the direction of our sun. So I'm going to call this sun direction. So that is going to go, and instead of actually I think, and we'll get to it when we get to it. So this is going to be the direction that we're marching in, and essentially what we want to do at the end is we want to check if the distance estimator has converged or diverged. So if it's converged, it means we've hit the object on the way to the sun, which means the object is blocking it from seeing the sun. But if it has diverged, it means like it's big. It means that we have, or it means that it has not blocked it. So the sun is hitting it, or the sun rays are able to reach it. So we're going to do less than, and I'm going to add a tolerance of like this. Actually, sorry, greater than. This is just checking if this distance estimator, the output of that, is greater than this value. So if it's less than that, it means that we're really close to the object, so we might as well be touching it. If it's greater than that, it means that we're probably far enough away that the sun is hitting it. And then that is going to be, I'm going to mute that. And that is what we're going to multiply this by. So that's going to be the shadows. So let's see how that looks. Oh, fun. It's going crazy. So this allows us a unique opportunity for figuring out what the fuck is going wrong, which is always fun. So it looks like we've inadvertently done something bad. Aha, that's what it is. We didn't put our direction into our direction out, so it's returning 0, so this direction vector is going to 0. Now it's also being wonky. Ah, I see. Gentlemen, make sure you configure your outputs properly. I just made an oopsie there that cost us a couple seconds. Alright, here we go. Back to normal. Now let's see how this looks. Oh dear. So sometimes it can be a little bit funky. So we can see sort of the impression that we're getting something happening over there, right? So what we might want to do is we might want to find this normal vector and just sort of push the position out of the faces a little bit so that we get a little bit better of a result. Because we are using imprecise SDFs, or SDFs, by the way, are signed distance functions. That's just distance estimator. So this noise texture is not a precise distance estimator. This part is. Or, sorry, not an exact one. It is relatively precise. So if we march this ray out from the faces a little bit, it'll make it a little bit easier to detect the shadows. So let's do that real quick. So we can just use a scale. I'm going to scale this by like 0.01. And then we can add that to the output or the intersection point. And that's going to push it out a little bit, and that should theoretically fix some of our problems. Yeah, there we go. So now we can see we're getting these nice shadows, and then we can also add this shading back in, and it's going to be shaded like a little bit more of a real object. And what we might want to do is add a little bit more detail here. It's pretty fun. I'm going to take that away so you can see a little bit more. So obviously this is imperfect and not very good, but you can see sort of how it's shaping it. It's pretty sweet. So we could also, let's our distance estimator out here. See how it affects with more. And there's obviously a lot of these artifacts and stuff. This can be solved, by the way, through a lot if you have higher samples, or in fact, actually, not in this specific case. This you have to, since we're using imperfect distance estimators, you can instead scale this down a little bit, like maybe 0.5, and you need more samples, but it's not going to give you those artifacts like you do get in this, which is always fun. Yeah, so that's a little bit better, and then we can add in a little bit more detail. And I'm keeping this at relatively low samples or low steps so that the computer can keep up, or EV can keep up. But you can go nuts. And I wanted to show you before you go. I'm about to wrap it up, but I want to show you what I've done in Shader Toy. So it's going to take me a second to find this, because, So this is done in Raymarching. This is obviously a significantly more advanced implementation. But by the way, Raymarching is what allows you to render these fractals. And you can see you're getting a lot of... so this is sort of hybrid technique. So it's using the light transport principles of ray tracing, which is all this bounce lighting and the Monte Carlo, but it's using Raymarching to evaluate the intersection points. And you can zoom in, all that fun stuff. It's pretty fun. Anyways, yeah, that is it for me. I will cut the stream there. Actually, before I go, anybody have any final questions? check VC text. Nobody's got any questions? Alright. I will cut the stream then. YouTube people, I'll see you guys later. Have a good one.